Well, hello. Good morning, everyone. I want to welcome you back to the Waste Conversion Technology Conference and Trade Show. My name is Dennis St. Pierre-Charles. I'll be moderating this morning's session, which is entitled A Review in Waste Conversion Technologies. First off, we're going to have Erik Wist, who's the Vice President of Juno Technology, presenting. And the presentation is entitled Juno Technology, Recovering Today, Repurposing Tomorrow. Erik, it's all yours.
All right, thanks. Hey, good morning, everyone, and appreciate you coming out to learn about Juno Technology. David McConnell was originally scheduled to be there in person. Unfortunately, he came down with COVID earlier this week. Good news is he's on the mend, but we wanted to give his voice a little bit of a break today. So the bad news is you're stuck with me for the next 30 minutes. I've got a handful of slides to run through here. I'm going to try to knock that out in about 20 minutes and then save some time for questions at the end. A little bit of background about me. As I said, I lead commercial development for Juno. I've been at Georgia Pacific 12 years. That's our parent company. Been working on Juno almost that whole time. And where I thought is, let's kind of kick this thing off, with an overview on Georgia Pacific, because that's and how we develop something like Juno. So we're a large pulp and paper company headquartered in Atlanta, Georgia. We employ about 30,000 people across 180 facilities. You've probably seen a lot of our brands before. So like Dixie plates and cups, Angel Soft and quilted northern paper towels or toilet paper, Brawny paper towels. If you've seen buildings constructed, often they're made with our materials. And we produce a lot of boxes to ship goods across the country. If you think about a pulp and paper company, recycled material and recycled paper is a core raw material for us. So we recover about 5 million tons of recycled material a year. We use about 2 million tons of that internally in our operations, and then trade the other 3 million to other paper companies across the country. And we reach as far as 50 countries to collect and recycle that paper. So if you think about us as a company, we've got about a century of experience in building and operating large pulp and recycling operations and trading commodities globally. And that's really the capability we've built off of to build and bring Juno Technology to market. So let's talk a little about then, kind of the problem we're solving, because we're not just going after paper. I mean, what we've kind of found is we're looking at a technology that can reduce waste to landfill. And if you think about landfills, I mean, that's, as everyone probably in this room knows, has been the disposal outlet of choice, or maybe not of choice, but the primary disposal outlet in our country and in really most of the world since the beginning of waste management practices. But at the same time, communities less and less want to have landfills built in their backyard. Companies and residents are trying to send less waste to landfill. And as a result, it's getting harder to permit new landfills, and there's just a general desire to send less to them. So if you're in the Northeast, a lot of your waste has to travel as far as Ohio, South Carolina, Georgia, because there aren't landfills in the state anymore. And even more broadly across the country over the next decade, just based off of currently operating assets, 8 states, those assets will be completely at capacity. And over the next 6 decades, that's true across all states. Of course, more landfills may be built, but it's getting harder and harder to do that. And so we need to find alternatives to send our waste. And the good news is, I think that when you look at what we are sending to landfill, a lot of it's recyclable. So just kind of looking across this, paper, plastic, metals, those all have commodity value in our market. And if we can recover those, get them out of landfill, they can be put to better use. Food can be composted, anaerobically digested, yard trimmings can be composted, even glass as outlets. So, when I look at the waste stream and even what we're processing at Juno, over 2/3 of it can be recovered, reused, recycled, and really, 80-90% of it can be diverted. So we're really optimistic, and that's That's what we're out to do is recover those resources that are going into landfills and put them to their highest and best uses. So what's Juno? Where did we start? How's a paper company develop Juno? Well, it started over a decade ago, and it started with us looking at all that paper going to landfill. So 25 million tons of paper goes to landfill a year in the U.S., and we realized, if we could tap into that, that could be an important new stream for the paper industry of a raw material. So we started with paper cups and developed a process that could take paper cups, deal with the plastic lining, recover them, and realized, not only it's difficult to get just paper cups in. So we said, well, what if we could take all the waste from, say, a fast food restaurant? And so in 2013, we built a pilot facility in Savannah, Georgia, which is, kind of the infancy of what is now Juno, and started taking waste in from fast food restaurants and realized not only could we recover paper, but we could recover plastics, metals, and even turn the food back into renewable biogas. And we said, well, hey, if we can do this for fast food restaurants, can we do it for other commercial sites? So we started bringing in waste from office buildings, airports, stadiums, running it through, and had the same impact. We were able to recover up to 90% of what was going to landfill in those sources. So we got pretty excited and realized that really the only way to prove this out and validate it is to have a commercial scale installation. So kind of set off, and in 2020, we started building our 70,000 ton facility, which is located in Toledo, Oregon. And as you can imagine, I mean, that was not for the faint of heart during, the pandemic, trying to build that facility with everything that was going on in the supply chain and some of the fires on the West Coast. But we were able to get it built on time and get it started up in early 2021. And here's just a couple of pictures of the facility. It's in, as I said, in Toledo, Oregon. Its ultimate goal, our North Star, is to recover up to 90% of what we process. And we realize that's going to take some time to get to that 90%, but I think we validated already that we can get there, diverting waste from landfills and incinerators. And so the way the process runs is we're taking in MSW. So, we don't want to touch recycling. What's being recycled should continue to be recycled. What we're going after is the black bag, waste that's in the trash cans going to landfills. That's brought into an offsite facility, and then we ultimately bring it over to Juno, where we autoclave it in a tailored autoclave. We call it JunoClave, where everything's sanitized, the paper's pulped up, and we hydrolyze the waste. We then feed it into a proprietary wet separation technology that lets us separate the fibers and organics from everything else. And then it's kind of a conventional MRF on the back end to pull out metals and plastics. And I'll show you guys a little video. Here's the facility itself. Those are bales of waste going in. We're not going to bale in the future, but at this site we wanted to because it's co-located with our paper mill. You can see the MSW. This is our feedstock coming into our offsite transfer station, where it's dumped on the floor. We do a visual inspect just to make sure there's nothing hazardous in there. And then it is dumped into a coarse shredder. And we do a very coarse shred just to deal with fabrics. And then we come out and we bale and wrap it. And again, we bale and wrap it because it's going to a paper mill. And we just wanted to be, extra safe kind of the first go around and make sure it's contained. The bales are fed into the JunoClave. You can see it rotating there. It's kind of like a cement mixer that applies heat and steam. So it's also a bit like a steam cooker or a pressure cooker at home. Inside, as this cooks, the paper's pulped up, food is solubilized into a liquid. And everything's sanitized, and then we discharge. And so you can see here that the brown kind of flakes in there, that's clean brown pulp. And the challenge in the past has been how to get that out, and that's where we've got a proprietary wet separation technology to separate out the pulp, and we also wash away the liquefied food. And so what you see coming out here is then what's left, the solids, which is plastics, metals, there's some textiles, wood, those sorts of things. We run it then through a series of processes to dewater it some. And then it basically goes into a MRF where we're pulling out metals and then ultimately plastics. You can see the non-ferrous or the ferrous coming out there, which are currently being sold, as well as the non-ferrous metals. Meanwhile, the fiber and the liquefied food is sent over to our paper mill, and we're able to, through a series of proprietary screening process, pull out a clean brown pulp, and the food is sent to our aerobic treatment plant. And this fiber goes into boxes that you see here, and we're actually just now starting to market Juno fiber to our customers. So boxes made with Juno fiber, diverted from landfills, and we're creating a kind of true circular kind of story on the West Coast of being able to take garbage, pull out fiber, and then put it back into boxes that are sold back on the West Coast. So we're pretty excited about that. Here's just kind of a schematic overview. I know it's busy, so I'll just run through it quickly. This is of our kind of full-scale systems looking forward. So as I said, we'll continue to have that number one in the top left receiving and prep area. We're not going to do the baling and wrapping anymore because this will actually be on site. The facilities will be standalone at the edge of cities. Waste will be tipped, dumped into the shredder like it is today, fed into the Juno clave like it is today. We move into that sanitization wet separation step 2 as it's discharged from the Juno clave, and we're able to wash away and separate out the pulp and food. And so it moves kind of to the bottom left to that phase 3 that you see. The liquefied food will be sent to an AD system and converted into renewable biogas that we can either put to the grid or use internally. The thing that's really interesting about this is the only thing we're sending to that AD system is a very organic rich liquid stream. So we actually hydrolyze it in the autoclave, which means we get 25% or more energy out of the food than you ordinarily would running it through an AD system. And also because we're sending such a pure stream to it, there's very little sludge that's created relative to kind of typical AD systems. So it's a really efficient process for handling food, any residual food that's left in the waste stream. And we think this will be pretty interesting as more and more states look at organics programs and organics mandates. We can bring in food contaminated containers as one-off loads. Any food that's kind of left over and fed into the system is going to end up in that AD system and converted into renewable biogas. At the same time as that food's washed away, we're going to have same thing that we're doing today, but we're going to dry that paper into pulp bales, and then it can be shipped globally for sale. So again, we don't have to be co-located with the paper mill. We can be near a city and then ship the paper globally from there. If you kind of go back then and say, hey, one path out of the sanitization, out of step 2 was to go, to recapture the fiber and food on the left. The other is the solids to the right going into step 4, which is, the conventional MRF. So we're pulling grit out. We're using metals and eddy current to pull out ferrous and non-ferrous. And in future systems, we're going to use optical sorting to pull out polyeth, HDPE, PET, and polypropylene. And so if you think about all that, you think about pulling out, food, paper, high-value metals, high-value plastics. That's at least 2/3 of the waste stream that's beneficially recycled. And then what's left, if it doesn't have market value, it actually has a pretty high energy value. And we turn that into an engineered fuel. And when we've done some testing on that, it's cleaner than a biomass fuel, has a really high energy value, and we'd either send that offsite to cement kilns to replace fossil fuels, or in some instances we'll have on-site energy production, and we're actually energy positive. So overall, it's a pretty efficient, system, and the design is to take products and get them to their highest and best use, and then as high up the waste hierarchy as we can. And so overall, if you kind of think of the waste stream, I mean, it's just under half. It's water, food, that sort of stuff that gets turned into biogas. Roughly 20% paper, 20% plastic, 5% metals, and then kind of a 10% other sent to landfill. So, the big question is, great, a lot of people can do this on a small scale. How about on the big scale? So we started up about 15 months ago. We started deliberately kind of running slowly, 5 days a week, 8 hours a day. If you also think about that time, we were going for commercial waste, and that was in the middle of the pandemic, and airport, stadiums, restaurants, office buildings, they're all empty. So we actually started processing residential MSW. We were a little bit nervous about that just because we hadn't done much of it before. And with a couple of minor tweaks, we were able to successfully process that. So then that fall, we went to 4 days a week, 24 hours a day. And then in November of 2021, we went 24/7. We're shooting to be over 60,000 tons a year at this facility. That's kind of our goal. We hit that the very first month, going 24/7 full time. So that was, and every month since then, and you can see every quarter since the end of 2021, we've hit that 60,000, and actually the last couple of months we've hit 70,000. So we're really pleased with the production of the facility. Our operators that come over from the paper mill say it's actually easier to operate than our paper mill. It's an incredibly automated system, and this is built on those decades of pulp and processing and recycling experience we have as a company. And so, you think about diversion rate, right? So we pull from waste from all over the state of Oregon. Whenever we bring in from municipality, we'll do a characterization. Here's an example of one we did for Marion County, which is in where Salem, Oregon is. So it's a 400-ton sample we ran. You kind of look to those numbers I was talking about earlier. We get about 17% fiber, 3% metals, and then about 20, just under 30% is kind of organics and treated water, all that gets diverted, reused. We just started washing our grit and doing some trials to send that to a lightweight aggregate. We think that's going to get us another 3%. And so out of the gate, we've reduced landfill by half for anyone who's sending us their MSW. And we haven't even put in the high value plastic sorting yet, which we think will get us another 5 to 10, even potentially 15%. And so that gets us to that 65% recycling rate of waste going to landfill, if not higher. And then sending the rest to, we'll ultimately start sending the rest as an engineered fuel, which can get us to over 90% landfill diversion. So we're pretty excited. We're in the city of Toledo, Oregon, where we're headquartered, where our plant is. We take about 95% of all their MSW generated. And in the year we've been running, we've taken the recycling rate from 23% to 66%. So it's just been a staggering improvement. And like I said, we still haven't put in the plastic sorting and some of the other stuff that we've trialed offsite and we know works. So we're really excited about this technology. What we're trying to do is really slide in under that recycling and expand how much is recycled. We want reduce and reuse to continue to grow. We want source separation to exist and continue to grow. And what we want is what's not being pulled out today, what's going to landfill, what's going to be burned. And we want to recover as much of that as we can to increase the recycling rate. And then what's left, if it can't be recovered, if it doesn't have recoverable value, we'll either turn it into energy or we'll landfill what's left. So we're really trying to expand, the top part of the waste hierarchy. When you think about carbon footprint, that's always a question, is how much energy going into this. The good news is it's a pretty low energy system. Our biggest energy draw is the motor on our fan that creates negative pressure in the building. So it's the Juno, Oregon is pretty low energy facility. And then when you think about keeping paper and food out of landfills, those are the largest methane generators. And then recycled metals, a lot more efficient on the economy than mining virgin metals. we end up offsetting about a ton, and this is kind of our initial estimates using the WAR model, a ton of CO2 for every ton of waste processed. And to just put that in perspective, so 70,000 tons at Juno, Toledo, and Oregon, that's equivalent to the carbon sequestered by about 86,000 acres of U.S. forest in a year. That's a forest about the size of Las Vegas. So we're talking real carbon impact, in addition to the recycling and diversion rate. Now that we've got this facility in Oregon up and running, and really feel good about where it is, we're looking to grow globally. So I mean, the U.S. and Canada are core markets. We're already in discussions with a couple of different sites here. And then also we're looking pretty heavily. We've got an offering on a site in the UK, and we're looking at a few sites in Australia. And you can see these are the other markets we see certainly global opportunity here. I mean, anywhere a waste energy plant makes sense, we make sense economically. So we really see a lot of growth opportunity for us to build, start up, operate these facilities. And the last thing I'll say, and then kind of open it up for questions. We've got the 70,000 ton system on the West Coast. Future systems are going to be the same, only instead of one Juno-Clave, we'll have 4. So if they're modular, we'll just modular it up, gives us a little more scale. Ends up being about a 330,000 ton system or 1,000 ton a day system. Standalone system that we'll put on the edge of cities to collect their waste and recycle as much of it as we can. So that's what we're looking to be near cities of about 1 million people and build these 1,000 ton per day systems. So that's it. That's kind of what I had, and I'll pause for questions.
Thank you very much, Erik. Does anyone have any questions? Okay, sir, here in the front. Just a moment, we're getting the microphone to him, Erik.
Hi, Erik. Good morning. Thank you for that. Aside from MSW in terms of a feedstock, do you have any applications that go beyond MSW?
Yeah, it's a good question. So, I mean, the system was designed for MSW, and it's really what works best. But we've done some trials on MRF rejects, and so depending on the MRF and the I guess characterization of the rejects, that's a potential. And we've also done some source separated beverage containers, so like aseptic packaging, things like that. The things that are difficult to recycle, we've had some luck and some trials doing those. So, we think that it's a pretty versatile system, and are always willing to have a conversation about different side streams.
This is Tim Flanagan. Thank you very much for your presentation. Is 1,000 tons per day the minimal amount of tonnage and throughput for your facility design?
It's a good question. So that's our optimal size, and that's really kind of what we want to focus on here. In the next few systems that we do. That said, as we co-locate at different brownfield sites, so if we co-located at a paper mill, if we co-located wastewater treatment plant or something, those synergies can help make smaller systems make sense. But our focus, I'd say, over the next 5 years or so will probably be those 1,000 ton a day systems.
Anyone else have any questions? Okay, well, thank you again, Erik. We really appreciate you contributing today and being here with us.
Sure thing. We really appreciate the opportunity.
Okay, next up, we're going to have Michael Kleist, with the VP of Business Development and Marketing for Sierra Energy. And he'll be talking about converting waste to profits and products with the FastOx gasification.
Hi, how you doing? Good morning. As you mentioned, Michael Kleist, VP of Business Development at Sierra Energy. I'll start off with what we already know. There is a lot of waste being produced in the world. Up to 2050, 3.4 billion tons of waste. That creates a lot of methane. Methane is a climate pollutant. This is sort of the area that we are attacking. I think all of the technologies here, how to solve the waste problem. So what is Sierra Energy? We are based in Davis, California. The description of our technology is a high temperature, ultra high temperature, fixed bed, updraft, oxygen blown slagging gasifier. So that's where we fit. I'll talk a little bit more about what that means later. We are based in Davis, California. If you look on the top right, we have a fully integrated commercial scale demonstration facility in operation that is at Fort Hunter Liggett in Monterey, California. And below on the bottom right, we do have in our office in Davis tooling facilities. We make our own lances. We do a lot of testing on site. We've received several awards. California Energy Commission, the Army helped us grant funding to build that facility at Fort Hunter Liggett. So what are we doing? As a gasifier, we can take, being high temperature, a variety of waste streams. So our focus is on being able to take mixed waste. So that's MSW, that's biomass, that's medical waste. All of these types of waste in a mix is actually good for our system. We then, in FastOx gasification, turn it into a synthesis gas. Then once you have a syngas, you can then create a variety of end products, and we'll talk a little bit about those later. On the right side, this was part of an investor slide we did earlier, so it's talking about how we'll make a ton of money in the future with large systems. On the bottom left, we did receive Series A funding led by Breakthrough Energy Ventures. That's that Bill Gates, Jeff Bezos, Save the World sort of GHG type fund, and Cox Enterprises. And that was critical for us. We talked a little bit yesterday about having a facility and having a demonstration facility in operation to prove the technology, particularly for customers, is critical. And that kind of investment and validation is just huge in getting to that, us to that stage. And we do have a variety of partners on the engineering, Rockwell Automation for our control systems, so ready to actually take this technology commercial. So where do we see ourselves fitting in the game? Obviously, you should be recycling. So we are 100% in favor of that. You should be doing composting, anaerobic digestion for the wet waste. We've heard a lot about pyrolysis. You should also be doing that when the feedstock stream, particularly plastics to plastics, when those fit, that's great. We like to look at ourselves as taking whatever's left. And that, and particularly in the United States, is the game we are looking at. Overseas, where they don't have the capability to do a lot of the processing of waste, we really can take just a shredded waste stream. I'll talk a little bit more about the types of feedstock, but we're good for that whole post-recycled bit. So feedstocks that we have tested. So before we got our first grant funding for that demonstration facility at Fort Hunter Liggett, we had a unit, DOD-funded Renewable Energy Testing Center in Sacramento, and we ran through all of these different types of waste. So tires, industrial waste, construction debris, biomass, MSW, medical, simulated medical, and things like batteries. Now, these materials have been tested in our system, but you definitely would not take a bunch of batteries and dump it in. What we're showing is that in a mixed waste stream, you're gonna have some batteries. You may have sharps. You're gonna have nylons and textiles and sneakers and these types of things. And in a mixed stream, that is okay for us. You're not gonna generate any energy out of batteries. If you put them all in, we would never do that. But we can take it if they do get in that stream. And based upon the testing of this feedstock is why we got the funding from the California Energy Commission and the Army. Now, so we're focused on taking that waste and turning it into a synthesis gas. That's what our technology is doing. Once you have that synthesis gas, as I mentioned earlier, you can do a lot of things with it. Now, hydrogen is highlighted because in the first couple of projects that we are getting into, the end product is going to be hydrogen. But you can do things like ammonia and fertilizer, RNG, methanol, et cetera. That doesn't mean all of these are economics. This is economically viable. These are things you can make from syngas. What I am seeing in the market in real projects are that RNG, methanol, and of course hydrogen are the three value end products at our system size, which I'll talk about in a bit. There are neat things like proteins, so you can go ahead and take syngas to proteins. A lot of those back-end technologies are not really commercial ready. Electricity, in fact, is the easiest, but when you look at the decreasing, wholesale electricity prices, I don't really see that being a good end product for us. So these are really the project developer is looking at what end product would be best for their market. And that is a value of syngas that you can, tune yourself to the local economics. So this slide is a little bit just showing what would be the volumes of output if you put a bunch of our systems together up to 1,000 tons per day, right? So on the far left, you're looking at creating 31,400 metric tons per year of hydrogen, right? We are commercializing our gasifiers at 100 tons per day. Our first projects and our sweet spot are around that 200 to 500 tons per day system. But this was to show that really if you were going to do something like Fischer-Tropsch liquids and some of these others, you need to go huge in order to make those economics work. But for methanol, hydrogen, and RNG, that is not the case. And that is why we see those being more valuable. So how does the technology work? So I described it earlier as an updraft fixed bed gasifier. So what happens is shredded waste goes into the top of the system. We inject steam and oxygen at the base of the system. We reach this high temperature of 4,000 degrees in a chemical reaction of the oxygen with the carbon in the waste stream. So in this system, you're only going to get three things out of our technology. The organic material is going to go off into a synthesis gas, which you probably know is mainly CO, H2, CO2, and some trace others. The inorganics are going to melt. So if you've got metal in there, it's going to be slagging. Think like a blast furnace with molten lava coming out. You're going to have liquid metal and liquid stone. And that stone, once cooled, is non-leaching. So it can be used for sure as road base. There's a lot of interest in things like potentially in the cement space or asphalt or even roof shingles. Really what we're focusing on is making sure it's a vitrified, non-leaching material that can have an alternative use. And the interesting part is you see it when I'm talking about a fixed bed. So you actually have a bed of waste in that gasifier. And as certain materials go off into synthesis gas earlier at low temperatures, other materials and the inorganics will make their way down to the melting zone at the bottom. So that means it's about a 45-minute residence time in this gasifier. And the advantage of that is that when you put in batch feed, so it's a continuous batch feed, if a certain wet material or other stuff gets in there, it is not going to collapse our bed or do any trouble. You have 45 minutes in there to adjust that system. And that's critical when you're looking at a mixed waste stream where you're going to have a variety of different types of feedstocks going in. This is a close-up of the system at Fort Hunter Liggett. So the gasifier is on the right. The second bit is a polisher. So if you know anything about gasification and updraft gasifiers for sure, and you're looking at that technology, the first question you should ask is, okay, what about tar? Because gasifiers will create tar. How are you ensuring that that tar is mitigated or gone once you get into gas cleaning? Because you need that clean synthesis gas to go to those back-end products, right? So we have our own IP, proprietary tar mitigation technology. The gasifier is low maintenance because there are no moving pieces and high temperature zones. It is very much of a solid, robust, hollow vessel with that waste feed inside. I mentioned we are oxygen blown, so the value of that is, you have oxygen, you get a clean stream of syngas, you're not pushing a bunch of nitrogen through the system. And I talked about that tar mitigation, which is critical in our sort of system. So you look at what is Sierra Energy trying to do. First of all, again, another investment type slide. Pyrolysis really shouldn't be on here. It's not gasification, but people are asking us, how does that sort of compare? You look at gasification as high temperature and low temperature, is how I view it. And low temperature gasifiers have been around a long time. They are good. They do create an ash material. And if you put in things like biomass or really clean organic streams like that, that ash material may be able to be land applied. If you're putting anything toxic in there, you're going to typically end up with a toxic ash that needs to be landfilled. Plasma gasifier is the closest to us. They are super high temperature. They were actually designed for waste destruction, so it's good on destruction. The problem there is there's so much energy required to heat up plasma torches that they don't make much energy on the back end. And you're now seeing a lot of these low temperature gasifiers trying to add some plasma on the back end to vitrify that ash I talked about. So what are we solving? Really 4 key things that don't exist in this space. Number 1 is true heterogeneous, true mixed waste. So in the gasification space, if you know the coal industry, the British Resynergi gasifier is the known gasifier for a certain type of coal. So it's a great gasifier, but you can't put in municipal solid waste or mixed waste. And the reason for that is the second point, slagging. In a low temperature or other systems, there are different ash melting points of a feedstock. And so if you put a low ash melting feedstock into a low temperature gasifier, you get tar, and that's going to gum up the system. And so truly the challenge is to be able to take this mixed waste stream and have it be slagging continually, even with that mixed feedstock. So we do that. We have our own tar control technology. We actually turn the tar into some soot, water, recycle the soot back to our gasifier. And then the final thing is you have to have a high syngas yield. And that means you're creating energy to run the system. If you look at a process flow diagram real quick, where we fit is in the middle. So we're not doing feedstock prep and that kind of material on the front end. We are a technology provider. We are taking that feedstock, the widest range we believe of feedstock available, gasifying it, and then it goes into final gas cleanup to an end product, in this case hydrogen, and you would have a very clean stream of CO2 that can either be sequestered or upgraded to food. But that's where we fit in the process flow. So in a facility, if you look at a schematic, you would have the waste prep in there. We are the bit in blue. And actually we go a little bit farther into the gas cleaning. So what we're doing is taking that mixed waste, turning it into a tar-free, particulate-free synthesis gas that can then go into another end product. And so that is where we are focused. We also have the software controls that run that system and would plug into the plant's overall software controls. So in this case, it's super, super automated. We've got 2 people in a control room and 1 person on the feedstock side, and that's basically running the system. When we create some of that synthesis gas, it actually gets recycled to run the gasifier. So as long as you're feeding in a carbonaceous waste, we need that carbon to react with the oxygen, we will recycle some of that gasifier to keep it hot so it runs on its own energy. I mentioned our facility at Fort Hunter Liggett, so that is a fully integrated facility, and that's really crucial in this space because you're seeing a lot of technologies come out and the technology works, but when you start to tie it up into all the gas cleaning and things behind it, issues come up. That's where the tar and those things can come into play. So we have commissioned this facility. We operate this facility in campaigns, multi-day 24/7 campaigns on municipal solid waste and biomass. We are now doing that for our customers because they want to see their waste run through our system, and we can do that. The municipal solid waste that's going through is post-recycled, so like a 60% cellulosic, 40% plastic mix. We've also put some RDF through there. And that slagging, as I talked about, every customer needs to come in, see their feedstock go through, see that synthesis gas quality and volume, and that we are slagging. And that 75% on the bottom is the cold gas efficiency. So in our system, that's the amount of energy in the waste that ends up in the synthesis gas. So it's really efficient, and it gives us about a 22 to 25% parasitic load, and meaning that amount of the syngas is required to run the system. The rest can go to the end product. And so the next step for us, so that facility is a 10 metric ton per day facility. It's got a generator on site for electricity and a Fischer-Tropsch skid to demonstrate liquid fuels. I mentioned earlier, I don't see those as the two best viable outputs. So we're looking to work with the base to add a hydrogen on the back end and then supply a fuel cell to power their microgrid at night. So that's that partnership with the DoD. What we're doing are now operating hours, being able to test feedstocks for our customers, and operator training. So both for our customers and our own team, we can do the training there. And that system is being scaled up to 100 metric tons per day. That is the commercial level we're going to on our first two projects. One of them is 100 tons per day. The other is putting two of them together at 200 tons per day. And so, you know, this is a timeline of, it's taken a long time to get there. As I mentioned, we had to do the demonstration facility at the DoD Renewable Testing Center. We then had to get permitted in California. So even though that demonstration facility is on a military base, we're actually governed by the local Monterey County Air Resources Board and local waste. So we didn't get any favoritism there. So we had to do that, build the system, commission it, and we are now licensing that technology at that 100 metric ton per day gasifier. And we're providing that gasification aisle. And the two projects I mentioned a little bit yesterday we're getting into are both actually overseas. One is doing an ammonia plant, so combining electrolysis, wind and solar to create hydrogen. We'll take biomass and create hydrogen, use the oxygen and the electricity from the electrolysis. That really reduces all CapEx. And then take the hydrogen, in both cases will go to ammonia. Our CO2 will be reacted with ammonia to create urea. And in that type of project, even at our smallest scale, 100 metric tons per day, we're able to sell that hydrogen into the project at under $2.50 per kilogram. As you go up in bigger projects, that goes down. The other project is taking MSW and pyrolysis residue. So we work really well in conjunction with pyrolysis that takes that clean plastic stream. We take that mixed non-recyclable bit of plastics and take that feedstock, and it's going into hydrogen. So yeah, that was a lot pretty quickly. So if you have any questions, let me know. Lastly, I do have, my email's not up here, but I have business cards. So if you have any questions, happy to give you my card.
Thank you, Mike. Quick question, how is the slag removed from the base of the vessel?
Yeah, so at Fort Hunter Liggett, it's actually doing a manual, think blast furnace. So it's got that type of design where you have that molten lava comes out the bottom. We're actually doing manual tapping there because, as I mentioned, we run it in campaigns. In the commercial system, there are already auto tapping systems that come out, so that slag automatically taps. Some of it is feedstock dependent, right? So if you're doing a, you know, I didn't mention too much about the feedstock that we like moisture content, 20% and lower. We have waste heat that can dry some of that, but also the ash content in waste matters. The more ash in the waste, that's gonna turn into stone. So if you got a feedstock with a lot of ash content, and some biomass, for example, even has that, but or biosolids, that will create more slag, and then you know, obviously that auto tapping is critical. So you'd never manually tap in a real system. Long answer, but yeah.
Thanks, Mike, for the great presentation. My question is actually kind of piggybacking on his question. So why is it tar and not a char, since you are doing high temperature fixed bread And
Yeah.
it's an updraft gasification, right?
Right. Yeah, so in that high temperature gasification, that material is going to get to a melting zone, and there's actually that char melts, and so the inorganics, the char reacts with the oxygen, so the carbon in the char goes off and goes into the synthesis gas, and those inorganics melt. So it's all to do with that temperature level. And we don't create, you create tar in the system, and then you turn that tar into additional synthesis gas, because you can't have any of that tar getting into the gas cleaning section. So it needs to be super clean syngas going there. And the value of that is on the slagging part, is it allows you to take those, without creating an ash, those metals and glass bits and things, it's really hard, as we know, to pull that out of MSW. And if you vitrify it, and that allows you to take some toxics, that's the advantage there of taking that tar, taking it and creating that slag.
So is that where you were talking about the inert glass kind of material where you are doing the vitrification?
Right, exactly. So, when you look at MSW, certain plastics, like we wouldn't be good for 100% plastic stream because you need fixed carbon to react with the oxygen. But we're great with a high percentage of plastic. So some of those will go off, into a gas really quickly. You have other materials that go off into a gas at, higher temperatures. And those inorganic materials will make their way into that melting zone. And just think blast furnace for iron ore, right? It gets in the bottom, it turns into a slag, and it's vitrified. So you have no waste byproducts. You're getting a syngas, metal, or that slag. And that's been tested, TLCB testing, and lots of interest in what you can do with that. I think I'm always cautious there because you can adjust the chemistry of that slag by adding calcium carbonate or limestone or other things to adjust it. We're really just making sure it's non-leaching.
Okay. And then you showed a slide where they had the different hydrogen output. So do you guys have any vision about moving away from municipal solid waste stream, but deal with only tire, for example, because the tire had the maximum number of hydrogen output and the other stuff? How do you think, first of all, what is your vision going forward to a different waste stream, because tire is a commercial waste?
Right.
And then second thing, how do you think your system's output would be if you move from municipal solid waste to the commercial and industrial waste like tire?
Right. So we're really focusing on the gasification aisle, right? Being the most robust gasifier to take the widest stream of waste. So the project developer would be looking and saying, okay, we want to do a project on tires to something else. What we would be doing is taking and being able to show what our system does with tires and that higher output, because you're right, you would get more synthesis gas from tires than MSW.
Yes.
We want to show and have shown that we can take that feedstock and then deliver a system for that tar-free synthesis gas to that developer for that feedstock. And for tires, for example, you'd have more sulfur. So you'd be looking at, okay, how are you taking care of the sulfur in that gas stream? And that's the bit where it really changes. The gasifier won't change, but a bit more on the back end side would. And so that's when you work with the developer and we say, what's your feedstock? Let's bring it down, let's run it through our system. That's the value of a demo. We would probably have to beg the Monterey Waste Resources District to let us do tires with the Army with us, because we're permitted for MSW and biomass. But yeah, so does that answer the question?
Yes.
Yeah.
Thank you so much.
Or are you scaling up the gas?
No.
Are you doing multiple trains going from 10 tons to 100 tons? Or are you going to scale the gasifier up?
Yeah, it's scaling up. And in the gasification space, that thing gets just a teeny bit wider and a little bit taller. So it is not in that blast furnace space, and we're super, super careful on that scale up bit. Because we went from a 2-ton sample in the renewable testing to the 10 to the 100. There have been major failures in gasification. If you're trying to sit there and go, we're taking 10 tons, now we're going to do 600. We're doing that 100 ton per day vessel. It's a really clear, the engineering and design is already underway on that. And so that's a really clear, comfortable scale up. And then we would put several of those together to reach the 200, 500 train. And real quick, that we have made, as we've run this, we've developed new IP at that system, and that new, that 100 ton per day is incorporating some of the new IP learned there too, which is good.
Yeah, that was really interesting. Thank you. At the end, you talked about the ammonia project in collaboration with like electrolyzers. And I think you threw out a price for the ammonia that you produce it at. Could you repeat that for me?
Yeah, so in that one, actually the developer is looking at, okay, how much is it going to cost for us to bring that hydrogen into play? And so while we're the gasification aisle, so we have to look at our inputs, right? Our inputs would be oxygen, and then the output, we're producing that tar-free clean syngas, right? And it needs to be at a spec for them to go ahead and take the hydrogen PSA technology to separate out the hydrogen. So in that case, we're looking at the electrolyzer, we're getting free oxygen. So they've already looked at the project and say, if we give you free oxygen, the electricity is almost, we don't need much, but it is incredibly cheap. The feedstock coming in is, we don't count tipping fee, none of that's in there. It's just a free feedstock that they have local. And then we know our cost for the gasification aisle, and then we've done an FEL2 with Fluor on the back end on the hydrogen for PSA. So we know what that is, and when you put that together with those inputs, adding on that hydrogen technology in the back, and the fact that we don't have to compress the hydrogen, it's going right into that, well, to some degree, but not like for a, tube trailers to go on transportation. All of that comes into, we are able to go under $2.50 to give them that hydrogen.
Okay, great, thanks.
Yeah. Great, thank you.
Thank you very much. Okay, next up we'll have Brian Bauer, the CEO and co-founder of Resynergi Incorporated. He'll be talking about advanced decentralized recycling, environmentally beneficial and locally based recycling.
Thank you so much. I am honored to be here. I kind of came on at the last second to fill in, but we are so excited. We're late to the game in pyrolysis. We take a very different approach, or decentralized, much smaller, compact approach. We use microwave technology to do it. So I'll go through that, where we are. We're coming on to commercialization very fast. And then I'll talk a little bit about SB 54, which is California's initiative to really control what we're doing with plastics. And I am so honored to have this crowd who knows how to work with California, or doesn't know how to work with California, but has a lot of good discussion on it. So first of all, you're very familiar with the plastic situation. We're looking, like others are talking about the waste pyramid. We have a place in it, and we're working to get the 6% up to much higher recycling rates. And the definition of recycling is an ongoing discussion, but we have a strong play here in our decentralized locating where the plastic is. So we take our process to where the plastic is, whether it's on the ocean ships to clean the plastic, or if it's small rural locations that, 100, 200,000 city locations about that size and above we can work with. So there are hundreds of places this can be deployed. Like I said, we're a 7-year company, and 20 years is the common length of time before commercializing. We teamed with the University of Minnesota. They were at it for 10 years working on microwave technologies. So we adopted that, and they did a very, very large scale, for a university, a very large scale system. And with very limited modifications of that, we commercialized that, and now we're ready to go. So we do more than just pie oil. I'll show you the full spectrum of carbon numbers, and we actually have road-ready fuel that's going on trucks between the San Francisco area and Southern California here, directly into the brand new Dodge Ram trucks. So we're very happy about that output, but we're also very pleased to supply some of the refineries with our base oil. So a full spectrum. We do, I don't have a detailed diagram, but basically we granulate like others, shred the feed, and then it's just 2, 4, and 5. So we're very focused on that. I loved hearing the Nexus presentation by Erik yesterday. It's so important to focus on the feedstock and get that right. We have great partners characterizing that feed and sorting and so forth. So what we can take in there will improve over time, but it's so important to get it right in the first place. So the process, we're about 20, 25 times faster than your traditional rotary kiln, so we can be that many times smaller. So it's a fast pyrolysis. I think it was mentioned yesterday, it takes hours for a typical pyrolysis particle to go through a whole system. Ours is seconds. So we are into road-ready fuel within seconds, so less than a minute. Then we have the option of going through a catalyst. So really base oil, we don't use a catalyst. For really, really high quality, we use catalysts. And it's been a lot of work to create redundant systems to keep a continuous system going at all times. So we've finished that base unit. So basically the solution works on a footprint of about 1 ton per day, and we can configure that to any size. So our first deployment is a 5-ton skid, so with 4 reactor units on it. Again, that's with really high quality fuel, low energy. It's really low energy because of the microwave and how, just like your home microwave, it doesn't heat the whole rest of the place. It only heats just what you want to heat in the reactor. We'll scale at 5 tons, and we'll just number that up or horizontally scale like a server farm. And the economics are fantastic. Because you use that much less material, because it's 25 times faster, you're able to scale much more economically and much faster. So a big factor in all these plants to de-risk is speed to deploy. We moved our pilot unit from our headquarters to the Recology site, and we turned up in about 3 days. And we expect that with any number of a handful of 5-ton systems be able to turn up within days. Not months or not years or decades, but within days now. And there's no new invention. We're using the same footprint and repeating it over and over. So again, our advantages are much faster. That compact modular design, it's not only compact and modular, but it's flexible, so you can run multiple outputs. Down the road, we'll have hydrogen outputs. We'll have the question came up yesterday of high quality high quality carbon. We can provide that down the road, but diesel, gasoline, basic pie oil for chemical recycling, and then a very, very highly paraffinic naphtha that can run through sophisticated crackers further down the stage. It doesn't need to be refined before going through the naphtha chemical resin manufacturing plastic plants. We have a little data here on, and we continue to provide data. This is the most important thing, is the greenhouse gas output. From the highest level, if you're talking to California or anybody, it's what are you doing as far as greenhouse gases compared to the current models? And we do actually have a letter from Air Quality Management California that highly recommends us for chemical recycling. So they look directly at those numbers, and that's the way to do it. Now, all parties within California don't talk the same way, but we are navigating through this, and I'm glad we have teams of people here who can navigate that with us. This is our operational pilot plant with Recology, and we're just repeating that reactor right there. We recently reconfigured it into a commercial mode where we're producing 24/7. So we now able to run weeks at a time, 24/7. And we recently switched gears to team with a couple major players in the data world and with major refineries to characterize all the different plastics. So again, we're focused real hard on the 2,4,5s and the good streams, but we're also looking at all the future contaminations and how that impacts our system. These are carbon numbers I mentioned. They're matching what you see at the pump. In some ways, we can be better match the ASTM distribution that's suggested. So I won't go through all this, but we have road-ready ASTM fuel, and this is what's being put into trucks going up and down California. Naphtha, again, there's two ways to provide chemical recycling liquids. One is base pie oil, and then work with the refineries, and they'll take that to the level it needs to go to for ethylene crackers or naphtha plants that take it and make resin. As I mentioned, we have a highly paraffinic naphtha, and we do that by adding a second stage of catalyst. And depending on how we configure this and run this, we can go for very high levels of hydrogen. But right now, the goal in the industry is to get at least 50% of the highly paraffinic naphtha out of a system like this. So we're hitting that now. This is probably another year or two before this very high quality naphtha is ready for production like the diesel, but very good progress. And all this work has been done through grants with the Alliance to End Plastic Waste and Plug and Play and those players along that group. The greenhouse gas calculation, we use the GREET model in California, present mode versus this future mode of operation. And it's about 68% when you go from end to end from making naphtha production through to the resin. If you look at similar numbers for the diesel, it's about 60% less greenhouse gas production in the production of diesel. So this looks great, right? And but a lot of California and some entities, they look at if you've got plastic, and just look at the front end of the plastic. If you were to do something with it, what are the greenhouse gases produced versus what if you just buried it in landfill? And it looks better when you just look at that narrow slice. It looks better to just bury it in the landfill because you're not putting out greenhouse gas in this refinery production. The reality is if you're Mother Earth looking at a much higher level, this is better to do the pyrolysis into fuel because the net effect, you're not drilling, you're not refining the way the current process goes. So a lot of discussions will go, and we will keep applying for it. Just to summarize again, super high efficient volumetric heating of microwave allows fast pyrolysis. We're modular, really fast to turn up. We use a real conservative number more for permitting and so forth, the 3 months to deploy, but it can be as fast as 3 days. In the decentralized approach, this could be in any state, even California, but we can be located at injection molding sites, distribution plants like Walmart plants, anything that's 5-10 tons a day or more. So this is profitable at 5 tons, very profitable at 10 tons per day, which is pretty amazingly small compared to all the numbers we're talking about. But it's because of that value in the plastics, the value at $6 a gallon in California for diesel, because we're providing actually very high quality, high value liquids. But then we can mix that up with base pie oil as well. So the idea is you can either provide fuel right on site, and so we're looking at doing that, again, like Recology sites and so forth, fueling their trucks, or you can send some of the base oil or naphtha to chemical plants that could be in other states. Now, we talked to Dan earlier yesterday, and we're trying to figure out if that's diversion credit or not if you go across state lines. But we just continue to provide our data and the numbers and do what we think is right. And we've even heard from Cal Recycle, look, we haven't figured all this out. Just go forward. We'll take your numbers and we'll follow you. Now, I can't trust that, but that's what we're doing. We just continue to show that we have good GHG and good results. So a minute here. How are we doing on time? Great. Okay, the clock went. So advanced recycling, I want to talk about SB 54 a little bit. This is pretty pathetic. This is the US. That's the production of the waste plastics in the orange, and then the green is how much is actually recycled. So even though there's really high value for HDPE, not a lot of it's recycled. So that will change with good collection. There's so many factors that go into that. But we will be addressing the number 2s that are not recycled and the 4s and 5s. This is a fantastic new way to look at the waste pyramid. Reduce, reuse, recycle. It adds a lot more categories. Pew Research went deep into this, and it's a wedge diagram that shows much better how to break this down, because there's a lot of different ways to address plastic. And starting from the top is the more preferable way to approach it, and the bottom, like ocean pollution, open burning, is the worst approach. So the reuse are near the top, and then what gets really interesting and open for lots of discussion is like chemical recycling in the middle there, and then chemical conversion, plastic to fuel. So those wedges actually are increasing over time, both of those is the suggestion, where it makes sense. Plastic to fuel isn't huge, but it's a sliver then. The chemical recycling, I would argue that should be even broken up, according to SB 54, broken up in two different categories. One is those things that are more environmental, the environmentally friendly to the world, and it's neighborhood friendly. There's a lot of concern about underserved neighborhoods getting the brunt of greenhouse gases and so forth. So I'll talk about how that should be split up, but that's growing as well here. So there's a lot of ways to approach this, and I hope we see more of this kind of look at the pyramid. Again, we address 2, 4s, and 5s, a lot of mechanical recycling. I love that chart Erik showed yesterday. I think it was Erik, that there's only 1 or 2, 3 lives with mechanical recycling oftentimes. You have infinite lives when you do chemical recycling, you just got to look at everything. I know it's hard to bring data to an emotional argument, Dan, but we keep doing it. So we're bridging that gap. We're making both high-value fuels, we're not afraid to say that, and also chemical feedstocks and feedstock for chemical recycling. There's the full-life, highly paraffinic naphtha that's in the works. And then this final slide here is SB 54. So what is SB 54 meant to do? It's meant to reduce the plastics that are out there. It's to recycle more. Look at 25% of the effort is just redesigning plastic out, but then 75% of the effort is in recycling more. And a big part of that is chemical recycling. When it first came out, there's this big roar of, oh, it bans chemical recycling. It doesn't ban making fuel, it doesn't ban chemical recycling, but what it does is it defines what's considered recycling. So, and American Chemistry Council came out and said, look, it's really broad and vague, there's no real good definition. And that's true, so we are moving forward and going to help define that. So these are the 4 bullets that they say need to be fulfilled. One is environmentally beneficial. So look at greenhouse gases, look at the source of how your site is being fueled. So if you use solar geothermal like we do in our 2 sites, it's very clean energy. So it's not just the technology, it's how it's electrified or how it's heated. So then the second thing is public health positive. So it's the environmental health groups, the county, they look for what are the byproducts, what's in that char, what kind of ash, is it dangerous or not? So we continue to provide that data, and they also look at a 3-part test in California. Is it separated well? Is there less than 1% putrefaction? And is it less than 10% solid waste? So we meet those requirements. We provide job growth in these neighborhoods, and you go 20 feet away, you can't smell anything going on. It's negligible. And this kind of skill level is like taking people from low to mid skill level. So it's very beneficial to the local communities. And then it's non-hazardous. So no NOx, SOx, dioxins, furans, and the char is very benign. So we just keep providing the data, and we'll keep plowing forward, and we'll work with air quality management with our super letter, and we'll keep going. So it's not for what was the word? The weak at heart or the meek, but the faint of heart. So we will continue forward, and thank you. There's my contact information there. Happy to take questions.
Have the large-scale equipment manufacturers like CAT, John Deere, and the like, have they approved this diesel for use in their engines for landfill equipment or material recovery facility equipment?
So you're talking about the syngases into there? Oh, for the diesel, yeah. So we're working with a couple of those, and both I didn't talk about it, but we can use the syngas to cogen and run the system almost independently. So that's one way of using the generators, but the other one for the diesel, yes, we're working with Caterpillar and working with others. And we're going on ships, the California Maritime Academy ship, and doing some research there as well.
Brian, great presentation, thank you. So, what's intriguing about the small scale system that you have is that the emissions profiles are, they're also small. What kind of encounters and churn have you had with the regulatory people vis-a-vis your emissions profiles, because they are much smaller, because your scale is much smaller? How's that gone for you?
Really well. So with air quality management, we share the data, the greenhouse primary data. So we just continue to monitor that. Yep.
All right, well, if there are no other questions, let's conclude this session. Thank you, gentlemen. Appreciate it. We're a little bit early, so why don't we do this? Why don't we meet back here in 30 minutes and give chance for those of you that have to check out, if you haven't, to go do that now. Come back in 30 minutes and we'll conclude with the final session for today. Thank you.